Well, this section is mostly about using a calculator to calculate logarithmic quantities. There's really a lot of important information in here and some reinforcing of ideas that you learned in 12.3, which is why we're jumping from 12.3 to 12.5 to 12.4. So this is the power you would raise 10 to get 100. So this thing right here, its meaning is if you put it here, you'll get 100. So whatever this is, it's the power you raise 10 to get 100. So you should know that that's 2. Notice this is a shorthand version of this. Since we live in base 10, we have 10 fingers, and we go numbers 1 through 9, and then we have 10. It's kind of assumed that if there's no base there, the base is 10. So that's all well and good, but how do we do a problem like this? Well, this won't be 1 because 10 to the first power is not 90. And it won't be 2 because we've just discovered that 10 to the second power is 100. So it's got to be somewhere, this has to be somewhere in between 1 and 2, and where? Well, it's the same quantity as this, because remember, there's an understood base of 10. So let's go over to our scientific calculator. This is the Desmos scientific calculator, which is kind of convenient for me to use. And let me put in the log, and that's understood base 10, because there is no base there, of 10. And so I will get over to the main screen and put in 10, and notice it's a 1. And if I put in 100, notice it's a 2. And if I put in 1,000, 10 to the third power is 1,000. This is pretty interesting stuff. You can figure out a lot just by doing this kind of thing. But if I put in a 90, I get like 1.954242509. So what happens if I put in, for instance, 1.954 and do 10 to that power? So I'm now going to do 10 to the power of, and then I'm going to put in this thing, 1.954242509. And this is a rounded off version. This is a rounded off version of the logarithm base 10 of 90, and so it's not quite enough. But notice it was good enough to get me almost to 90. I mean 89.9999991 is just a hair's breadth from 90. So this thing here, this logarithm base 10 of 90, really is the exponent you'd raise 10 to get 90. It's really true, and that's an important thing to remember. So what about the logarithm base 3 of 10? This is the power you would raise 3 to get 10. So if you're trying to figure out what this is by using common sense, then you're asking yourself this question: what power would I raise 3 to get an answer of 10? And the answer isn't 2, because 3 squared is only 9, but it's certainly not 3, because 3 to the third power is 27. So it's going to be 2 point something kind of small. So we could sort of idealistically come over here to Desmos, and we could try for another row, and we could try to do the logarithm. So let's go to the functions. Logarithm base 3, but notice there's only 2 kind of logarithms. There's a log without anything, which is base 10, and then there's the natural log ln, which is base e, which is like 2.7 something or other. And there is no log base 3 or log base 4 or log base 5, and so what in the heck are we supposed to do? We know that this is going to be a number in a little bit bigger than 2, but we don't know what it is. So the makers of the calculator know something. They know that there's a change of base formula that you can use if you know what you're doing. And the makers of the Desmos calculator want to encourage you to know what you're doing. So they did not give you log base 3 or log base 4 or log base A, because they know that you should know this. The log base 3 of 10 is the log of 10 divided by the log of the base. So it's the log of the result divided by the log of the base. And the interesting thing about this is that these two logarithms can have any base you want. They could have base 2, they could have base 3, they could have base 4, they could be base 10, they could be base e. As long as these two logarithms match, they can have any legal base that they want, which is very interesting. So I'm going to leave it this way, which means it's the logarithm base 10, doesn't it? That allows us to use Desmos to calculate this. So let's go do the log 10 divided by the log 3 and see what happens. We have log of 10, which we should know is going to be 1. And then divided by the log of 3. And notice we thought it would be a number a little bit bigger than 2, and it turns out to be this number right here. And so now let's see if in fact this is a power that you can raise 3 to get 10. So we will do 3 to this power 2.095903274. And notice it's getting pretty close to 10. Yeah. Now let's try something here, just for the heck of it. It's going to be hard to key in, but I'm going to try to key in this log base 10 divided by log base 3 thing right here, right now, just to kind of see if I can. So we have function log base 10. And I'll move over a little bit, divided by log base 3. Notice this. I raised 3 to this power and I got exactly 10. The software is good enough to give me exactly 10. So when I put in this approximation, 2.09590372274, it got me close to 10. This one gives me exactly 10, which is kind of interesting. This, the natural log of 10, is the log base e of 10, where e is that number that's about 2.7 approximately. It's kind of like pi. It goes on forever, never, never. And why we would use e, we're really not going to discover too much in this course, but if you were to take pre-calculus or calculus, e would become your good friend. So the question is, how could you calculate the natural log of 10? Well, you go to functions and there's a natural log button, and then you put in 10, and it's about 2.3025, etc. So let's just check it out. Let's see if e to, oh, well, I guess I could have used the e to the x button. Oh well, I'm not going to now. I'm determined. Look at that. I got close enough that it just said, ah, heck, and rounded it off to 10. So sure enough, e to this power is 10. So what does this natural log of 10 mean? It's the power you raise e to get 10. And we're raising e to that power, and we get 10 as proof of concept. It's really important. So how do we graph a logarithmic function? Well, logarithmic functions are going to be the inverse of exponential functions, and we kind of have a vague memory maybe of how those exponential functions looked. They kind of looked like this. And if logarithms are going to in general be inverses, then they got to kind of look like this. They just sort of have to. But specifically, how do we graph this? And that is with a calculator. We're going to put in x values that make sense. And since this logarithm is a power you raise e to get an answer, when you raise e to a power, you always get a positive answer. E to the anything is a positive number. E to the negative 1 billion is a positive number. E to a million is a positive number. E to a 1 power is positive. E to anything is a positive number. And so this natural logarithm has to be positive, and so we can't put in 3 here for x because we would get the natural log of 0, and how can a power of e be 0? So I started at 4, although really I could have started really close to 3. I started at 4 and put a 4 in here, and 4 take away 3 is 1, so I get the natural log of 1, the natural log of 2, the natural log of 3, the natural log of 4. So the natural log of 1 is 0. We knew that. The natural log of 2 is about 0.7. So let me come over here, see if I can do this. This is 0, this is 0.7, then I need 3 and 4. So 3 gives me about 1.1. 4 gives me 1.4, so I have 1.1 and 1.4. And on your calculator, you could press the natural log button if you could find it, and that would work out pretty well. So the natural, so when x is 4, we're getting an output of 0. And when x is 5, we're getting an output of 0.7. And when x is 6, we're getting an output of 1.1. And when x is 7, we're getting an output of 1.4. And it looks like something's happening here, but we're not sure what. Now I kind of think maybe it will go down and approach this 3 sort of like this, but I don't know, I'm just guessing. I don't think it's ever going to quite touch 3, so what could we do? Well, we could come up here and put in 3.1. So that'll be the natural log of 0.1. And we could come over here, and we could put in 0.1, and that's negative 2.3. What about 0.01? Negative 4.6, and so it just keeps getting more and more and more negative. So it looks like this idea was correct. And is that kind of the inverse that we were expecting? Well, it's kind of the inverse that we were expecting. Seems sort of right. So this is how you sketch the graph of a logarithmic function. You just depend on your calculator keys to help you evaluate the logarithmic part of the function.